Hello, everyone. Thanks for joining. How are you finding session so far? Good. Okay, that's interesting. And what was your favorite topic? Okay, yeah, you can eventually come out and talk about it. Right. So I'm Soujanya Konka. I'm a senior solutions architect with ISVSA India team. But apart from that, I do take up OpenSearch conversations and deep dive discussions with customers across India. And for today, I'm going to talk about primarily vector search with OpenSearch and how you can build some of the common solutions that you use in a day-to-day life, and how easily you can build them using the LLMs that are rapidly evolving and emerging in the markets, right? Okay, I'm going to move here for the slide navigation. Okay, so when you talk about vector search, where do you find the use cases? It's mostly in terms of improving customer experience, or it can be relevance or performance. Now, performance, because a user at an interface expects latency, the higher precision, and also when I say user experience, how personalized they can be. Take an example of Amazon.com. I know most of our presentations on search, we try to go back because it's a massive customer, and with petabytes of data, dynamically you also we also input a lot of data on the fly with the queries as well. The filters get added on the fly. We have a wide variety of use cases that come in with Amazon.com. Using that as a context, let's talk about more about where do we find vector search use cases. Starting with lexical search, we have seen even this has evolved. So it can be typing with a certain keyword. You know what is the metadata that you associating with a particular search, and that gets matched with the metadata that is associated with the index, and you get the results. Now, what's missing here is the intent. So we do not know what is the intent behind your search. Now, I can say it's a brown dress for a party, or a red dress for a certain occasion or a season. You're giving some more context to it than your regular textual search. And that's where personalized experience comes in. Think of it like a user who is aware of okay, what is this person like, and what were his or her previous search looking like, and at the real time as well. Whenever you are selecting, for example, if I say the same brown shoe for a particular occasion, you select one of the images, you must have noticed that the search results, they refresh. That's because whatever you have clicked, maybe it's the color, it's the size, it's the range or the price associated with it. Backend filter has been applied on the query itself, getting you more appropriate results, and all this is happening in the real time. Now, how is that happening? There are particular specific ways of doing it by using pre-existing plugins, or actually defining your own model IDs using the neural plugins, etc. We'll talk through that, how vector search has evolved in OpenSearch itself. Now, talking about semantic search. So in this example, you'll see a difference between how you will see the results coming in whenever, again, it's nothing but the simple translating it to an embedding, which can be a text or an image, and then you're using the space to measure the nearest vector, which can be L2, L1 distance, or a cosine distance, to find out what is the nearest closest match and display them. This is exactly what happens when you hit a platform. Now think of another use case like a Q&A or a chat bot. You need more personalized responses. It's not like you go there, you ask, put an image, hey, give me all that's matching this particular jacket. It's more than that. So that's where RAG comes in. So you will see me moving from one topic to the other and see how we have evolved in each of these vector search topics. Now I'm talking about a multi-model maze search. Now you've seen this feature, I'm sure you must be using it as well. You can search along with text as well as an image. Let's say you like a particular chair, you click an image, and plus you can also say, hi, I want the same chair but in white, maybe in some other material. So you're giving both text and particular image. So it's going to translate each of these fields into a vector, and then it is going to apply a semantic search in the backend and get you the results which are more appropriate to what you're trying to ask. And that's exactly what you can do with multi-model search. And think of use cases. Let's say you're uploading a document which has images or it has any information which is in a unstructured format that needs to be translated to a vector. And it essentially is not textual all the time. So that is where multi-model search can be used. I think I'll skip few slides, whichever are repetitive. Evolution of search. Now, this is exactly what I was referring to from the story I was trying to talk through from this beginning of the session. So we started with keyword search around 2012. And then we evolved into incorporating certain easy-to-use plugins like the LTR plugin or personalized ranking that you can do with models that can be pre-trained with your existing data, and you load the model to an OpenSearch and still apply the results on the fly to get the personalized ranking responses. That's the personalized plugin. And the next one is we have also added semantic search and hybrid search. And also, you can see in the conversational space, it's again a lot more that we do right now. The hybrid search or the neural sparse search and the RAG workflows that you can build with any LLMs. And it can be LLMs that you bring in, or it can be using the SageMaker connector. Let's say a model is available, has been released. DeepSeek is a recent example, or it can take any other model that has been released. It will be available in SageMaker in a 2 weeks time frame. And then you can build this connector, use it to build a complete RAG flow. So that's where we are at the current conversational search phase, you can say. I'll talk about a few of these. So that's the lexical re-ranking, regression, and generative AI era where we are in. Talking about a simple search interface. So this has multiple things. I know you're looking at maybe the search results. It's a common experience, but if you take a closer look at it, there are multiple results coming from different queries. So on the left-hand side, you will see multiple set of filters, like the rating field or the range filters. And on the right-hand side, there are some ads or promotions, recommendations. Now that can be closer match to what you're trying to search. So this can come from personalization. It can be your previous history, or it can be your current search that you're doing, and the closer match of results that you may want to try. The actual organic responses is what you see at the bottom, and these can be a combination of lexical plus semantic as well. Now, so all this goes into constructing a complete personalized response interface or that you see for the user. Let's break each one of these and let's see how we can achieve them. Okay, let's go. All right, I'll let the slide completely fill in. All right, so here the search services. Now here I was referring to more of lexical search and how you can also improve relevance with n-gram and boosting techniques that we have, and then emergence of a KNN vector. So here you will be using the KNN vector to where you use a number k, you do the splitting of the how you can actually group the results and get the more appropriate results to the user. ML Common, it gives ML Commons. Now, with the emergence of ML Commons, it gives you a flexibility to host a model and gives you a model serving layer. So you can bring in a model that is already supported with OpenSearch or bring your own model. So that's the benefit of ML Commons. And then we have added neural plugin. Now here you can create ingestion pipelines, search pipelines with a model ID. Now this model ID, as I mentioned in few of the other examples, it can be any model. It can be an external model as well. But a neural plugin gives you a model serving layer to build your ingestion, to build your vector search pipelines. Serverless vector engine. Now serverless also provides the vector capabilities apart from the provisioned service that we have. Generative AI Assistant Toolkit. Now, this is an interesting feature. If you haven't tried, I strongly suggest you to go ahead and explore that. So you can also, it can give you recommendations on the queries. Let's say you're working with logs, and there is an increase in the network or data transfer that's happening. So you can ask it to write a simple PPL query and to identify, hey, what is the particular service where the data transfer is happening, or what is the particular VPCs that we need to navigate and run a particular query. So that can be recommended by the Generative AI Assistant Toolkit. Speaking about plugins and ML integrations, so I'll start with the middle one, learning to rank. So here, if you see the evaluation model, we were talking about the having ready-to-use plugins. So in this ready-to-use plugins, we use a pre-trained model which has your historic data. Now this historic data can be user data plus also the interaction data. How many clicks has this customer performed earlier? You use that, you train the model, you deploy the model, and simple, it can be something like, and you use that to display the results in a rank based on the priority. And the vector search embedding and storage with the KNN and neural plugin. Bring your own model with ML Commons. Now, this is what I was referring to, where you can bring in models, not the ones just that you can see here, for any unsupervised model as well. Or you can also bring the bird-based models, Hugging Face, or also the models from Bedrock. You can create, you can use the model ID, reference it, and create your own ingestion or search pipeline. Let's move ahead and talk a little bit more on these personalized rank results. So there are two ways of doing personalization with managed services. So here you see Amazon Personalize. Now that's a managed ML service where let's say in your organization you do not want to overload your data scientists. There are certain algorithms which can be run or use cases that can be built with your analysts or engineers. So that's when you can use completely managed ML services. Amazon Personalize is one of them. What you do is essentially just get your data. So it's your user data and the product data. It can be a product data with the catalog and information of its metadata, the region of usage, what is the color, brands, etc. And what is the interaction history of the user and the catalog data. And then you supply it to Personalize. Personalize pre-trains the model. It creates a custom model output, and the endpoint will be available for you. So that endpoint will be referenced by OpenSearch. The moment you get the results out for a particular search query, you can use this model endpoint to re-rank the results and get a more personalized response. So now think of a scenario like the same product search or a Netflix search where you have your pre-existing history available and it's going to re-rank and present the results to you. So that's exactly where you can build an entire recommendation pipeline without even writing a line of code. So in simple search queries, you should be able to build this out. But again, it requires you to have a history of the earlier interaction data. So that's the only catch here. Similarly, you can also use the LTR plugin. Now, actually, this slide covers what are the different interaction data that you can think of for a user interface. The click streams, the user engagement. Hey, what was the engage time? What was the scroll time? And what is a certain parts of the video which was skipped, or abandonment rate, the churn rate that you want to predict for this particular customer, brand category, preferences, etc. So all this becomes your interaction data. And essentially, yeah, and any user interface, it doesn't need to be just the product search or from the media search, etc. Anywhere where you have the user preferences getting captured, actually. Let me move on and show you the how the LTR plugin works. Yes, so you build the model, you prepare the training data sets, and you add the mini feature values. You can do some hyperparameterization as well. So if certain values like region takes preference or season takes preference, you can also add that hyperparameterization, and you prepare a final judgment list. Hey, my results are going to be in this particular format. And in a particular time range, you're supposed to show, let's say, a campaign code or a discount code that you want to display. So all that responses can be modified and tunable as part of this particular plugin. Moving ahead, let's talk a little more about what are the different semantic search capabilities available on OpenSearch. So these are the four at a broader category. So semantic search. Okay, let me put the slide. Speaking of semantic search, is again relies on your data. Now, the better your data, the better you choose the fields that you need to map to a vector, you will attain more accurate results. And just a little background on what these vectors are and how do you build these, because you'll need to understand what are the algorithms, the engines, and the space type when you define a vector within vector index within OpenSearch. So that's important to choose what is the dimension and what are the fields that I'm going to use to generate this particular vector. So essentially, vector is nothing but just a refresher for just to bring people on the same page. It's a point in an n-dimensional space, and you will see my vector represented with a floating point numbers arranged in the form of an array. And it can change based on the number of dimensions you choose for your vector. It can be 768 or 300. Yeah, the recommendation is usually you start with a vector space of a lower range and then keep increasing and also adjusting the other knobs or parameters when you design your vector. What are the other knobs and parameters? It depends on what is the algorithm you choose. And then you adjust these parameters to ensure you're getting the accuracy, recall, and latency as per your use case. Yeah, so once you have decided on what's the dimension, what's the vector, the embedding model that you're going to use, you also need to understand what is the distance measurement that you're going to use. It can be popular is the cosine, similarity, Euclidean, or the L2 distance. So this is nothing but simple math. You're going to just identify what is the closest point in the n-dimensional space. Now these points are nothing but the same images or the text that we were talking about earlier in the previous slides. So that translates to a point where you're going to compare and get what are my closest results. And yeah, so this is an image which is giving all the unstructured data that can go in, and we can create vectors out of it using the embedding models. So it can be videos, images, audio files, or a textual data combined with a video or an image as well. So it can be, we have seen multiple use cases. Primarily think of an enterprise with multiple such data. within your organization, and you're creating an assistant within your organization where am I eligible for a particular leave for 10 days period. So internally, what is it going to do? It's going to search a lot of textual information which is present against your profile, and also what are the eligible criteria, etc. Essentially, it's going against the completely scanning through the knowledge base and finding the results for you. So let's think of that as one of the scenarios when you're saying, okay, what is the enterprise data search whenever a vector search is applied in that case. Okay, so this is a very interesting slide. You can it actually summarizes many use cases where you are bringing in a vector search use case. If you generalize it and forget the part where you are seeing the sparse vector. It's a kind of a template diagram where you think the raw data can be of any format. You're converting using an embedding model. Now, maybe for the documents, you will need some more models to parse the data and to break it down, chunk it down, and then convert it into an vector, a final vector that can be a dense vector that can be stored in a vector database. OpenSearch is one of the vector databases, but there are other options available in the market too. And once you have the data stored, you can the next set of use cases arise coming from you. Hey, do I just want to do a search, or do I want to continue indexing the data in a frequent manner? If my data is rapidly changing. Think of it like a chat use case or an audio file. So every day there can be data that can get indexed. It converts to vector, again goes back to the vector storage, and then you will have the live users who are also querying it in real time. So at the back end, the structure remains the same, and yes, you can always extend this with a RAG use case, adding another summarization model at the end after fetching the results from the semantic search. So yes, so this you can think as the base architecture with neural plugin. Now, if you remember the previous one, you saw the embeddings, the text data or the source data that is converting into encodings. Now you will see with neural plugin, we've made that easy. You can create both your ingestion and search pipelines, bringing in your own encoding models. So with the neural search plugin, and that's where, because you're creating your own connectors, and that has the heavy lifting part of creating the connectors has been removed. And yeah, so this is another, I would say, a benchmarking slide, which talks about how do you choose the HNSW and IVF-based models, or what is the algorithm that I need to choose. Now we are going a little deeper into the vectors, talking about how do you store these vectors, what is the algorithm that you use to actually store these vector into an index. So that's where we need to understand what are the two different techniques OpenSearch uses, the KNN and the ANN. So exact KNN actually works for smaller data sets. Now think of a simple example. You have a bunch of beads, and if I ask you to put them into a smaller packets, which exactly matches them, let's say beads of 100 different shades of colors, it's a difficult task, right? And imagine if the beads are growing from thousands to millions. It becomes even more difficult, and it becomes resource intensive. So that's the reason we suggest exact KNN actually works for a smaller data sets, and it's more brute force because you're actually doing a matching and putting them before. Of course, the best part is you can apply pre-filters, but with approximate KNN with the larger data sets. Usually when you see vectors, we are talking about millions, or there are a few customers who also come up with billions of vectors that they need to store. And that's when approximate KNN works for them. With HNSW and IVF, you should be able to reduce the resource pressure that you're going to put with KNN, but we'll see how HNSW and IVF are also different. Even between them, you can cut down the amount of memory that is needed based on the technique, how it's going to store each of these vectors and process them for query. and it applies post filter but by default, but efficient pre-filters are also available. So it takes a decision in terms of what pre-filters and post-filters can be applied. So that's a high-level understanding of what's the differentiation and when to use KNN and ANN. So this is an example which is talking about the KNN part. You will see painless scripts added. I'll skip each few of these. Yeah, and this is approximate KNN search. I just want you to focus on the part that there is a model ID, and you create a processor where you are going to create an ingest pipeline. So you create an ingest pipeline, you select the model ID, and then you put in certain methods here. So you see the HNSW, what is my engine that I am going to use, and what is the space type? That is the difference, how I'm going to calculate the difference between those vectors. So this is how a simple query of an ingestion pipeline looks like. And then you're creating an index on the other side. And moving ahead, yeah, I think this is the neural search query again. Yeah, okay, from the quadrants, let's move on to the other vector search type. So that's the hybrid search. Now think of use cases. If you remember the slide where you have, where I showed you multiple parameters that come into play when displaying these results to the user. So there was recommendations, there were ad results, there were organic results, and there were a few filters on the left-hand side. Now there are few cases where we feel where you will understand that everything cannot be solved by semantic search. You definitely need some lexical search which works with predetermined keywords. So you do not need to burn GPUs and get the semantic results out for every single query. So that's where we brought in the hybrid search query. It combines both the results of lexical search and vector search, and it applies something called as normalization and puts the results in a ranked manner for the user. So that's called hybrid search, and you can say it combines, it brings you the best of both lexical and vector search. So this is an example. Yeah. I think this slide summarizes very beautifully what is a hybrid search. So BM25, the textual search scoring mechanism, plus the KNN scoring. So when I say scoring, you are doing a vector search, and the results are associated with a particular score. Now, let's say and what happens with these two is the scoring is actually 0 to 1 and 1 greater than 1. Now, in order to get the response in a format that is more meaningfully putting the results out, you need to normalize each of these scores and put them in an order so they can be ranked. That's where the normalization of the score happens after fetching the results. And then it combines and puts the results in a document, puts the documents, which is the responses in an order. So this is where the hybrid search, this is the high-level flow of hybrid search pipeline. And even in the ranking, again, you can, there are other fine-tuning that can be done with displaying your ranked results. So we'll see if I have few slides to that. Okay, yeah, here's an example. So yeah, you can see this normalization processor, and it's giving you the min-max technique of displaying the results. So yeah, you can tweak a little bit on the normalization as well, and if you want to increase the boosting of displaying the results, so you can have some control in modifying the queries also. It's just not the blending the scores and displaying the results that can come in with hybrid. Yeah, and the next one, I think we also spoke a little bit about the multi-model search earlier. So this brings you a capability of searching with multiple unstructured data. It can be both textual images, text plus video. So and you can use two different models as well to create this particular vector. Let's see if I have an example. So yeah, this is, I think this is more visual example where you can see, yes, a user is actually giving an image plus some more description about the item. And interesting is it's not a single line description. You can give an entire image metadata. It can be machine, yeah, in this case, if you see the particular apparel plus what is the fit, what is the material type, and some more details. Everything gets translated to a vector, and it applies against each of and it starts doing a semantic search in the backend. Okay, I have an example here. So here you see the vector, especially focus on the highlighted place where you can see the image description and the image binary. So essentially we are using both the description and the binary, and that's getting, so that you can see the description and the image that's getting converted to a vector. And you're putting it into an index. And creating the particular vector embedding. That's the field which has the vector associated with this with both the fields. Yeah, and then you're applying a search. So you're getting the results wherever using this particular vector embedding field, and you're giving a query text which says wedding shoes, and it's going to give you a response which is much closer, both with the text and also with the image. Yeah, this is exactly what's happening if you correlate this queries and the previous image, this is exactly what's running in the backend. Yeah, and neural sparse search. Now this is, I'm not sure if you're familiar, sparse is also a popular encoding technique. And what you do here is a lightweight encoding. So instead of translating your unstructured data into a vector, you rather convert them into a bunch of tokens. And each of these tokens are semantically matching the word or the text that has been inputted to convert into an encoding. So you will see also a weight associated with each of these words. Now, for example, yeah, here in this case, let's say it's converting each of these will husbandry lead to global warming. The entire text, what are the different words that are part of it, plus what is the actual context that we are referring to. Okay, we are referring to a temperature, we are referring to warming, we are referring to global, maybe weather conditions, etc. And then it associates these weights and stores them in the descending order in your index. This is more lighter and less resource intensive compared to the dense vectors. And that's where you can use sparse search vectors for use cases where you think, yeah, you're not, where you have larger data sets as well. But we have seen customers using both sparse and dense vectors as well to achieve that better accuracy. Yeah, it can be both the ways. Okay, again, I have an example for the sparse. It's a very similar thing, but only thing for sparse encoding, you have a different set of models. You will see OpenSearch encoding model version 1, 2, which are already supported, and you can use those. Or you can use an external Hugging Face encoding models also, which are very popular. You need to reference them just the way we have seen other examples earlier, and it generates a model ID. In the same way, your input data, you're going to convert that and store it into one of the vector fields. The best part of sparse is you don't need to create a KNN index. It can sit in any of your existing lexical index itself, along with your textual data. So that's an advantage. And yes, that's a search query which is showing results for a red shirt. And it's referencing again back to the model ID, because at the query time as well, it's going to turn them into a sparse and match that to the tokens. Wherever the tokens, again, it's going to compare with the weights of the tokens. Wherever it's a closer match, it's going to give you the response out. Yeah. Okay, I will cover the architecture and then show you the demo. I think that's easier. Yeah, so essentially what we are doing is a trade-off between how many vectors am I going to are present in my corpus, which is my knowledge base, and what is the dimension. It's recommended to start with dimensions as low as possible, and plus you've also made a choice of, let's say, ANN and KNN. So when you say ANN, you choose the HNSW or the IVF based on how much your data is going to grow and what is your existing corpus, and then you come up with what is the accuracy and latency. Mine is a product search use case. For me, latency is important, and definitely accuracy. Or it's a chatbot use case, or I'm giving a results to a particular WebSocket. Then maybe my throughput is important. And the latency can be slightly higher as well. So based on those parameters, you can make a decision as to what is the particular technique that you're going to use from the 4 different methods that we just saw. And okay, let's see a little more. Yeah. This is another interesting slide which talks more about how does it work when you're storing vectors in the OpenSearch ecosystem. So at a high level, you know that indexes are divided into shards, and shards are further divided into segments. And whenever you ingest documents or update, it further creates these segments. And when we are talking about vector search, these segments are divided into vector native library indexes. So it becomes a subsegment. You can think of it that way, which is managing the vector functions of that particular cluster. And this is exactly how, if you map it to the memory requirements of a particular OpenSearch cluster, the half of it goes to a JVM, half of it goes to OS operating system activities. And when you talk about a vector engine that's getting vector search use cases that let's say ML Commons has been used, then in that case, we are extending we are increasing the memory of the particular cluster. And that's where we are actually dividing the available memory between the OS and also between the vector engine. And there are certain tunable parameters as well. This like the circuit breaker. Let's say we always suggest whenever you're putting your vector search use cases on a cluster, we suggest you go with scaling up and then think about scaling out. The reason is vectors are processed on the RAM, and you need more memory to put your vectors and run these search queries. We've also come up with the disk optimized feature, where your vectors can be offloaded to the disk, and your search also happens there. But this is an evolving space. So that's where your memory requirements are very essential when you're talking about these vector search use cases. And we have defined a math around, after you choosing your number of dimensions, the replica, the engine algorithm, what is the exact amount of RAM that you would need, which translates into the number of instances that you would need. So we have all that math publicly available, that you should use that as a parameter to decide what is your cluster size. So yeah, that's the background behind sharing more about the architecture. Let me, yeah. Okay, I think this is the preparation. Yeah. So speaking about the engines, now we spoke a little bit about algorithms, the HNSW and the IVF. The engines are InMSlib5 and Lucene. Yeah, the Facebook AI semantic search, the star that you will see. Because it supports all the algorithms and the quantization techniques also. Now we have brought in, as we are growing with, we have customers with growing use cases on vectors, and the volumes are also growing. There is need to optimize and quantize how you're storing these vectors, and that's where these quantization techniques come in. We've introduced few of them, which is the product quantization, scalar, and binary. And again, you need to choose based on how you want to break down these vectors and store them. is essentially what it's doing is it's cutting down the memory that is taken by the entire vector storage. And yes, and this is definitely essential because as you grow, as the number of vectors grow, we have seen customers actually growing from few million vectors to billion vectors for certain use cases. Think of the scale of Airbnbs, think of the scale of Make My Trip. So where definitely there is a lot of metadata, images, user uploads certain images. So that data is dynamically growing. You need to quantize and apply these techniques where you're actually reducing the total amount of memory consumed. I know that will be a deeper conversation, but do reach out if you have certain use cases on that front. I just tried to summarize this in case you want to take a quick capture of this image. This actually talks about choose the engine, you choose the algorithm, and then how you, based on your post filter, pre-filter, what's the dimensions maximum it is supporting, what's the explainability factor, and what are the different quantization techniques that it supports. So accordingly, you should be able to break your vectors down and reduce the storage. Yeah. Okay, let's, I don't know how we are doing for time, but this kind of summarizes all the knobs that you need to follow to improve your overall vector search performance. So when you talk about indexing in the sense ingesting, so you disable the refresh interval. Essentially, you're not allowing the primary to replica, primarily to copy the data into to the replica as and when the data is ingested. You disable the replicas to improve the ingestion throughput. Increase the number of indexing threads. Now, indexing threads is nothing but it matches the number of CPUs that you allocate to the cluster and ensure you have enough indexing threads if you're indexing heavy workload. Larger shard size, yes. Now we've seen a lot of customers. I'm sure a few of my colleagues would agree. There are customers with kilobyte KBs of data, and that they just blow up on the number of shard size. This increases the metadata associated with your storage, and unnecessarily whenever a query hits in, it spends a lot of time actually searching the right shard. So you want to avoid that. We normally suggest you go with 40 GB shard size if you're working with log analytics workloads, or if it's a search, you can start from 30 to 40 and iterate whichever is working well. And prefer larger instance types. Yes, as I mentioned, since vector search will require memory. Again, you'll have to do a basic math to arrive at what is the memory that I will need. So start with scale up and then choose scale out. And I would strongly suggest you can also look at the disk optimized feature. Talking about search, you reduce the segment count and the warming up of index, and avoid reading stored fields. Okay, yeah, that's. Okay, so this is one interesting tool. I was having conversation with someone outside. So let's say you want to run, we have spoken about multiple available techniques of running your vector search. Which one works best for me? And even under techniques, we are saying there are different algorithms. So you can actually use this benchmarking utility. That's the link. You can take a capture if you want. So what it does is it creates different indexes, and one with HNSW, one with IVF, one with certain dimensions you can store your vector, and one with 368. And then you come benchmark and get your results out that you can compare and take a decision based on your accuracy or recall that you would need. Okay, I just quickly wanted to show okay, hope you're seeing this. Yeah, a quick demo before we close. I thought this will give a better description of what we spoke so far on multiple different vector search techniques. So I'm here. Right. So here we are using a product catalog data set. This is a simple textual search. And in this case, I'm using a search comparison tool. You must be familiar with it if you have used the OpenSearch interface. So here you can compare the results with two different queries. And in this case, I'm just doing a simple textual search with the vector search, and because at the right hand side you can see there is a model ID, but on the left hand side we are just saying a simple textual search. You will see the results are more relevant when we are applying a semantic search with a model for a, I think this is cotton sheets, yeah, rather than just doing a keyword search. Let me go pick another example. Let's say, yeah, maybe a sparse search. If you remember, this is from one of the slides. It converts to a bag of tokens and weights for each of the corpus data. And then it goes and picks whichever is the closest match. So based on t-shirt with an animal image, you can see, yes, the one that's closest and it's ranking on top of my search results is actually giving you, yes, a t-shirt with an animal image. Versus the one that we are seeing on the left-hand side, it's a textual. It's actually doing a keyword match with the descriptions and the other fields of this particular index. Okay, let me quickly show another one, maybe. Yeah, multi-model search. Yeah, again, a comparison with textual search, but in this case, I think we are using a, yeah. Okay, let's quickly search. Using, again, the description and the image to convert into a vector, and this is the model ID. What are we searching for? Yellow curry dish, yes. So, yeah, you see the results are more relevant when we are doing a multi-model search. So, yeah, these are few examples that I wanted to share with you. But yeah, please do reach out to us if you have any use cases or would like to discuss anything. I'm also available outside at the podium if you want to catch up for any queries. Thank you for joining me today.